At the end of this construction of inlet velocity profiles, you will find a YouTube link, and here you have a little bit more advanced setup. So yeah, we have to do the commercial first. Here he creates sort of an inlet, analytical inlet velocity profile in a two-dimensional case, so in a square channel. So yeah. Come on. Here we go. So he has an analytical expression here for a solution, a flow inside a square channel. So we want to use this one as an inlet velocity profile. So he explains in detail how it's done, but it's roughly the same as what I've shown you here. Okay. Now for the final question here in exercise 2 for you guys. For this problem here, turbulent flow, we have a symmetry plane and then backward facing step. And here, initially, of course, you send in constant velocity, you give a constant k, constant omega, constant epsilon, which is probably wrong. If we want to send in a fully developed flow, or let a fully developed flow hitting the step, then we can't use just the constant values here and then just 1 meters here. This one then should have been somewhere over here if you want to have it fully developed before he hits the step. Expensive. How to produce inlet values which are already fully developed. Not analytically, this is for a turbulent flow. Hence we have to simulate it. So how are we going to do that? Well, for question C, I called it an optional extra, but definitely something you should spend some time on. How can we do this? Let us then go back to OpenFOAM, and we have, where are we? Go one back here. So I want to create now a one-dimensional flow from a solid wall to a symmetry plane, and I want velocity, pressure, k, omega, epsilon, whatever. How can we do that? First, let's make a copy of the original Pitts-Daly case. What should we call this case? We call it inlet 1D. Inlet underscore 1D. That should be okay. So now I have created an inlet one-dimensional case, but I started with the original Pitts-Daly. Okay, never mind. Now for the Pitts-Daly case, that was rather messy, backward-facing step and a nozzle and whatever. So there I'm already now going to use the block mesh that we had from this cavity case from last lecture. So well, let's go into the inlet 1D case here, and then I copy from our what did we call it, turbulent cavity, and I want the system block mesh dict. There we have the mesh, and I want that one now overwriting my block mesh dict in my new system, something like that. Then at the same time we can actually copy most of the zero folders as well. Let's take the entire zero folder. CP, turbulent cavity, zero folder, all the files there into my zero folder here, like that. So now I've copied a lot of the setup for the turbulent cavity case, mostly. Let's start with the mesh. gedit, and then we had system block mesh dict. So here we have the mesh. Here I have used 1 by 1 meters and then 10 centimeters in the Z direction. Yeah, why not? We can keep that one. And then I had 100 by 100 cells. Now I want this one to be a one-dimensional case. Let's start easy here. I use only 10 cells in the Y direction from the wall and then to a symmetry line. Then I don't need this advanced X stretching. He can hardly stretch anything with just one cell, so here I just have a 1. So now for the simple grading, nothing in X, nothing in Z, but in the Y direction, yeah, we have the same stretching. Well, actually, we don't need it that complex, do we? If I have a symmetry line at the top. No, let's do this much, much easier. I have 1. And then what should we have in the Y direction? The top cell should be huge. The bottom one should be small. Okay. Let's take 5. We do it easy. There we have it. That should be good enough. I stretch only one way. Then the top wall, that's not a moving wall anymore. What should we call him? Well, top. Why not? He is a type symmetry plane. Oops, like that. And then I have the bottom. And he's of type wall. Well, I don't have all of them, do I? Now we have to remember how was open foam organized. Well, you have a 0, 1, 2, 3, if I recall correctly, and then you have 4, 5, 6, 7. So 0, 4, 7, 3. That should be the left face. That's actually the inlet, isn't it? So let's copy that one to the inlet, or move that one. We're going to need an inlet somewhere up here, for instance. What about that one? The number 2. I never remember all this. I think I have a cheat sheet here. That one. 0, 1, 2, 2. Yeah, 1, 2. Yeah, that one should be the outlet. Okay, move that one as well. Up here. But then we have the bottom. That one should be okay. So I have an inlet, something like this, and then we have what's the type? What's the type here? How am I going to do this? I only have 1 column of cells. So what do we have in the X direction here? There we use the cyclic boundary condition. So this is going to be of type cyclic. That should be okay. Cyclic. When you are using cyclic, you say, now at the inlet, he's going to be cyclic. What's his comrade? Cyclic against what? Then you have to tell him, well, he should then talk to, and then another boundary. So, and that one, they call it the neighbor patch, I think it is, yep. The neighbor patch. That was the inlet. That must then be the outlet, like that. And then we have phases. Something like that, yes, and then close parentheses, and then we should be done here, I think. Like that. So there you have the first inlet. He should then be cyclic, talking to the outlet. Then we have to do the same for the other one. Let's see now, where are we? I can copy this one. Inlet, and then we create an outlet. Like that, but then it's this one we should have here instead of that one. So the outlet, he has to talk to the inlet. Here we have it. They should talk to each other, should be okay. Top, symmetry plane, bottom, solid wall. Okay? And I only have 10 cells. So sadly, I don't think he will now accept if I try to run block mesh. We can try it. So you see he crashes. And the reason is here, is your mesh up to date with split cyclics? What are you talking about? With the split cyclics. Did I write something wrong here? Cyclic phases. Oh, it should be correct, I think. Inlet, outlet. Yeah, I don't see any wrong. Where? Yes. Ah, something wrong here. Nay. Yeah. Neighbor. Thank you. There it went. So now that one is okay. We can try, but I don't think it works. Ah, it works. Wireframe. Yeah, so there we have our mesh. Very nice indeed. So only 10 cells, and we have stretched it. So of course it's the boundary layer that is going to be important. We're going to use more cells later on, but never mind that. And yes, this one is now three-dimensional, of course, but we only are interested in the Y variation here. Okay, so far so good. Now we have to, sadly, go through the different zero folders. So here now I have to do a lot of writing. I have to change all these to cyclic. I can show you one. I think I can cheat afterwards. Let's see now. Starting, for instance, never mind. Okay, thank you. Okay, for the camera viewers, then sadly the camera has been off, but you haven't missed much. We're just starting now to create a 1D case for creating inlet velocity turbulence profiles for say any case. But so far we haven't really made it run. Well, it runs, but what's going on here? Residuals are 0. except for the epsilon, which is quite big. And what about k? Well, he's quite big. Can anybody guess what has happened or what has not happened? Well, I can show you. Parafoam. And we can apply. And let's have a look at the velocity. And we can look at the end time. And yes, we have zero velocity. We have pressure 0. And we have the epsilon. Well, here has something down at the wall, but it's so you see, nothing has happened. Nothing at all. Why? Where is the driving force in this problem? I have a cyclic pressure, I have cyclic velocity. Nothing is going to happen, of course not. That's too bad, isn't it? How do we do that? Here is the trick. You have the option to put in a driving force times minus Rm to put in a driving force in such a way that you have an average velocity of 1 or 10 or whatever you want. Let me show you how that one is done. I think I had it in a different case here, and then here we have it. I'll just copy that one. And then I can show you. Inside my constant folder, I now put a file, it's called FV options. FV options, that is a file where you can specify sort of a given source. I want a mean velocity force. I want an external force so that my field U has a value of 10. Okay, why not? 10, that was the same average value as for the Pitts-Daly case, right? So we can use 10, fair enough. Let's then try to run and see if something happens. Where are we? Simple form. Well, he still went all the way up to 2000. But at least now something has happened. We have gotten some numbers here, but he has trouble getting the residual small enough. Let's have a look. Parafoam. Apply. And go to the end. So that was the pressure. Well, looks a little strange. Of course, we have just one-dimensional variation here in the y direction. But if you look at the numbers, they are practically 0. For the velocity, then we have something that makes sense. We have a high velocity, most of the region, and then a sharp boundary layer down here. A little too sharp, maybe. And then, how about our epsilon, and k, and whatever. And even the eddy viscosity we have. So yes, this is one way then you can produce, say, one-dimensional results. But is it trustworthy? Well, actually not really. First of all, if you can recall from the Pitts-Daly case, they used 1 inch as an inlet height. I have used 1 meter. So we have different Reynolds numbers. So the Reynolds number doesn't match. So that's definitely something we should change. Here I won't bother to do it precisely. If you want to change it, then yes, you have to go through this, look to the viscosity. So this one is 10 to the power minus 5. I have an opening of 1 meter. I have an average velocity of 10. So I have a Reynolds number of 1 million. Ooh, That was a little bit too much, wasn't it? Let's reduce it a little bit. 4 there, and then save. And for the U, no, not that one, sorry. The FV option, I go back to 1. Then I should have a Reynolds number of 10,000. It's a little bit more soft. That's one thing. Another thing, I have only 10 cells. And that is a little bit rough. So let's do 100 cells. And now let's see what happens. Where are we? Here. Yeah, let's get rid of those. Foam list times minus remove. And we have to create the mesh. And we simulate. Still didn't converge within 2,000 steps. But I would say the U velocity has a very small residual. Look at the V velocity. How the heck is that possible? I don't have a V velocity. Come on, for crying out loud. I mean, it's not possible to have a V velocity when you only have a one-dimensional mesh. Stupid program. So, how come? The problem here might be actually the way he calculates a residual. Typically what he does, he creates a first residual for the first step. And then he uses that one as a scale. So the residuals are non-dimensional. And if your first residual is 0, then he scales towards 0. So that can be actually a problem with the residuals. So we talk more about the residuals later. The other residuals here, they are actually quite fine. Okay, never mind. Let's have a look at the solution here. Para foam. Apply. And then we look at the velocity and we go to the end here. I have increased the Reynolds number, no, decreased it from 1 million to 10,000. So now we have a much larger shoulder, you might say, as we should. Makes sense. What about our turbulence quantities here? Epsilon, very narrow, close to the wall. What about K? Also very sharp, close to the wall. The pressure, again, he doesn't make any sense. He doesn't do anything in the y direction here, so forget about him. But one thing here, of course, we should investigate. What's my y plus? Just check that one. Simple foam, then minus post process, minus func, y plus. I only have one single cell downstairs, and it was 10. Actually, then I need more cells, or stretch a little harder if I want that one below 6. So that one should be changed. Okay, let's get rid of the results here. So what should we change then? We can stretch the mesh a little harder. I use 10. Okay. Now, here is one point. Remember what we are going to do afterwards with the result here. We are going to use them as input files, as inlet conditions in another simulation. Then we should have used the exact same mesh in the y direction as the original that we are going to use later. But here, never mind that. I just want this simulation to be okay. So I save this one. And then finally, since he refused to sort of give me a solution here, or a solution that sort of is converged, here is a little trick. Here you have a residual control. So the pressure and the velocities are sort of given with some numbers, and then for all the other equations as well. This u, you can actually split it up into two. Looking at the component at a time here, so I can have here ux and this one uy. If you just write u, he will use u magnitude. But now I have it for each component. But I use the same value. Let's see if that changes anything. Okay, we have to create the mesh first. Block mesh, and then simple foam. No, he still went all the way to 2000. Too bad. Let us change then. Remove the result, and then I change this number to okay. Take -1. Why not? Because I don't really care about the velocity in the y direction. It's not going to be a part of the solution anyway. It's going to be 0. So if this stupid program insists on solving that equation, be my guest, but I don't need it. So let's try again. He still refuses. That was a little bit strange. He should be okay now. Never mind. I think I have a solution to that one, but I will put it out for you later. Let's see the y plus. Now it's 7. Well, it's close to 6. I can accept that one. Never mind. So now say that I accept this solution. I'll put out a version for you that is a little bit more convergent. I have another one. Yeah?
Instead of the FV options, could you just put an internal field of 1, 0, 0 in the U file, and then let the cyclic boundary conditions do the job?
No. That's a sad thing. I mean, here you have to specify cyclic because you want a fully developed profile at each side.
Yeah, but that meant the uniform, internal field uniform at the top.
Here, no, but this is just sort of the initial values. So you can here, you can do the following. Internal field, I have here 11 and I have here -3. You can start with something stupid like that. And he will then just run and remove that. Anyway, you have the same solution. Maybe it takes a longer time, but no, it doesn't help. Yeah?
Is there actually copy the file with the opt? Where was that from?
Sorry,
This file you needed to copy.
Oh yeah, you need that file. Well, I'm not sure if you are allowed to use the same file if you have the same system. But I mean, the file name, that is called this FV options. So then you can use the find command and look, say, you can search through all the tutorials and see if you can find it there as a file. That's one way. Okay, say now that we accept the solution. Then, next step. If you use the exact same mesh as you have in your inlet, we are going to use this inlet, then this should be the same order. Then you don't have to look into the C files and the CY files. Then that's not a problem. But then what you have to do here is going to your solution and then say, for instance, now the velocity profile. Here I now have 100 internal points. Then you have to copy all of them and then glue it in as an inlet in your program. The same way I showed you earlier with this, the way we did it up here. So as an inlet in U, for instance, you just glue in the number of points that you have. No, not that one. Where was it? Here. Then you have to glue in your velocity components, and in the K file you have a K profile, and so on and so forth. How does it look? Quickly, we have time to that. Let's see now. Paraform. Apply, go to the end, take a plot of a line, and I want it from x point 0.5, 0.05, 0.5, 0.05. Here we are. Here you have the different values, and you see the epsilon, he peaks at the wall. Let's remove him here. Epsilon, where are you? Here you are. Get rid of him. Then we have a K. He's also peaking quite high on the wall. Get rid of him. There we have something. Here you have the turbulent velocity profile. So it's very narrow here close to the wall. This one doesn't look too good, does it? And then he sort of levels off. This turbulent profile I can accept, but not this wall treatment. So I still haven't resolved the wall good enough here. But we are on the way at least. The pressure doesn't really matter. This was U magnitude. Of course, here you don't have any difference between U magnitude and UX. They will be identical, of course. So yeah, we need to resolve the boundary layer a little bit better, but then we should have a decent 1D fully developed flow that can be used in another simulation as inlet profile. I'll put this one out for you on the homepage. Any questions? Yeah.
This file, where is the fully developed, where does the fully developed flow, where do we paste it in? Is it in the 0U file?
Yeah, if you want to use this as a boundary condition now, say for example, the Pitts-Daly case or something like that, then I open, I go to the Pitts-Daly case, we have it here, 0 folder, and say for the velocity U. Then instead of these two lines here, I then have to put in an entire list and then glue in all the velocities in there.
Okay.
Yeah.
When are you being assigned to groups?
Next week. Okay? Then we stop here.